Hey guys, Mr. Betts here. Let's go through the week 13 progress check. So first question here, we have a differentiable function with some information given to us about the function and its derivative at x equals 3. We are also told that g is concave down on the interval from 2 to 4, which also includes the x value of 3. And we want to know what is an approximate value for g of 2.6 using a tangent line to the graph of g. So first thing we're going to do is write the equation of the tangent line. So we have a point here. This is going to be the point 3, 2. That's not a 2. 3, 2. So that's a point on the graph of g, but it's also going to be the point of tangency, so it's going to be on our tangent line. And then this derivative here is going to give us the slope at that point. So in point slope form, we have y minus 2 equals negative 3/4 x minus 3. And so that equation is going to be the equation of the line tangent to the curve. But remember, since that's tangent to the curve, it's going to be a close approximation of the curve around x equals 3. And 2.6 is fairly close, so that should give us a pretty close approximation. So what I'm going to do here is I'm going to write g of 2.6. And essentially, I'm replacing the y here with the g of 2.6. So that's going to be the y value on the line, which is approximating the y value on the curve. So is approximately equal to 2. So I'm just moving that minus 2 over. Minus 3/4 times 2.6 minus 3. So I replace the x with 2.6. 2.6 minus 3 is negative 0.4. So this is going to be equal to 2 minus 3/4 times negative 0.4, or negative 4/10. I would think of it as negative 4/10, and that's going to help with simplifying. So that's going to be 2 plus 3/10. So that's equal to 2 plus 3/10, or 2.3. All right, so this is an approximate value of 2.6. I want to point out that we're using approximately equal to here, and then equal signs the rest of the way because each step is equal to the step before it. But with the approximately equal to up here, that's going to tell us that g of 2.6 is approximately equal to 2.3. All right, so that narrows it down to C or D. The other thing we have to do is determine whether it's an over approximation or under approximation. And so we're told that G is concave down. So if we were to graph G, we know it's concave down between 2 and 4. So at 3, the tangent line, not a great line, but you get the idea. The tangent line is going to be above the curve since the curve is concave down. So this 2.3 is a value that's on the line, so it's going to be a little bit bigger than the value that we get from the curve, so that's going to be an overestimate. Number 2 is really similar, so I'm going to go through it a little bit more quickly, but we want to approximate g of 4.2 using a tangent line to g at x equals 4. So at x equals 4, we're going to be using this derivative here, and we have the value of the function at that point, so that gives us the point 412. It has a slope given by the derivative, which is 2.2. So we have y minus 12 is equal to 2.2 times x minus 4. So then I'm approximating g of 4.2. So g of 4.2 is approximately equal to, so the g of 4.2, replace the y there, 12 plus 2.2 times x, and x is 4.2, minus 4. All right, so that is equal to 12 plus 2.2 times 0.2. 2.2 times 0.2 is 0.44. So 12.44 is going to give us A. Another pretty similar one. So we have f as a function. The graph of f has a derivative given by this. It passes through the line 1, 2. It is concave down on the interval from 1 to 1.5. We want to approximate f of 1.2 using the tangent line at x equals 0. So the local linear approximation is just saying the tangent line. So we're looking for the value of f of 1.2. And so we're going to write the equation of the tangent line. So at the point 1, 2, and has a slope given by dy dx. So dy dx at the point 1, 2 is going to be 2 squared minus 1, which is 3. So we're using that derivative formula to find the slope at that point. And then we use that to write the equation of the line. So y minus 2 equals 3 times x minus 1. And so we've got f of 1.2 is approximately equal to 2 plus 3 times 1.2 minus 1. That's going to equal 2 plus 3 times 0.2, which is 0.6, and we get 2.6. So f of 1.2 is approximately equal to 2.6. That narrows it down to C and D. But again, we need to determine if it's an underestimate or overestimate. The function is concave down on the interval from the point of tangency to a point beyond where we're approximating. So it actually doesn't matter that we don't know if it's concave up or concave down to the left of 1. Just between the point of tangency and the approximation, we need to know the concavity. So again, since it's concave down, then the tangent line is going to be an over approximation. So the curve, let me try that again. Curve is curving down, tangent line is going to be above, so that's going to be an overestimate. Number 4, we're moving into using L'Hopital's rule now. And remember, L'Hopital's rule only works if our limit is in the form 0 over 0. So an indeterminate form, 0 over 0, or infinity over infinity. So the first thing we want to do is we want to evaluate the limit as x approaches pi over 2 of the numerator and denominator separately. So 3 cosine of x. Cosine of pi over 2 is 0, so that limit is 0. We also want to look at the limit as x approaches pi over 2 of the denominator, 2x minus pi. Note the use of my parentheses there because we have multiple terms. 2 times pi over 2 is pi minus pi is 0. So the numerator and denominator both independently approach 0. That gives us the indeterminate form 0 over 0. So we are going to use L'Hopital's rule. Let me clean this up here for a moment. So this is going to equal then, we're going to keep the limit part the same for L'Hopital's rule. And then we take the derivative of the numerator. Derivative of 3 cosine of x is negative 3 sine of x. And the derivative of 2x minus pi, the derivative of 2x is 2. And remember, pi is just a constant, and the derivative of a constant is 0. So once we've done this, once we've applied L'Hopital's rule, we want to try direct substitution again. And this time, if we use direct substitution, sine of pi over 2 is 1. So we get negative 3 times 1 over 2, and that's just negative 3 halves. So once we've applied L'Hopital's rule, we try direct substitution. If we don't get an indeterminate form again, then we get our answer. Number 5, this is going to be another L'Hopital's rule. We can kind of mentally check to make sure that it's going to apply. So plugging 0 in, we're going to get 6 minus 2 minus 4, that's a 4, which is 0. Sine of 0 in the denominator is 0, so it is 0 over 0. But again, we want to confirm that. We want to show that we know L'Hopital's rule applies by checking both of these limits. This is a fun one here, minus 2 e to the 3x minus 4, and the limit as x approaches 0 of the sine of 2x. So in the first one, e to the 0 is 1, so we get 6 minus 2 times 1 is 2, minus 4, that's 0. So the numerator does approach 0. The denominator limit, sine of 0 is 0. 0 over 0 is indeterminate, so L'Hopital's rule is going to apply. So we keep the limit part the same, and then we're going to take derivatives. We want to be careful here with our derivatives. In both the numerator and denominator, we are going to need to use the chain rule. So the derivative of e to the 4x is going to be e to the 4x, and then we have that inner function 4x, derivative of that is 4, so we have to multiply by 4. So 6 times 4 is 24, e to the 4x, minus, same thing is happening here. So when we take the derivative of e to the 3x, we're going to be multiplying by 3. So 6 e to the 3x. Derivative of negative 4 is 0, so that one drops out. And then derivative of sine is cosine. We keep the inner function inside, but then we have to multiply by the derivative of the inner function, which is 2. Now we try direct substitution again. This time we are going to get an answer. So we get 24 e to the 0 is just 24, minus 6 e to the 0 is minus 6, and then in the denominator, 2 times cosine of 0. Cosine of 0 is 1, so we're going to get 2 in the denominator. So 18 divided by 2 gives us 9. And the last L'Hopital's rule, this one, it's not as obvious that we're going to use L'Hopital's rule. However, we are trying to evaluate this limit, and we are already told that the limit of the denominator is infinity. We do need to look at what's happening in the numerator as x approaches infinity. So the limit as x approaches infinity of the numerator, f of x, is going to be... So as x approaches infinity, the first term, the 3x, that's going to go to infinity. And the 3e to the negative infinity, e to the negative infinity is 1 over e to the infinity. I'm using infinity like a number, but remember it's not really a number. So it's 1 over a really big number, and when we divide by a really big number, we get a really small number. So this term is approaching 0, but infinity plus 0 is going to be infinity. So our limit in the numerator is infinity. Our limit in the denominator is infinity. So L'Hopital's rule applies for the indeterminate form infinity over infinity. So applying L'Hopital's rule here, limit stays the same. Then we take the derivative of the numerator. So the derivative of f of x is going to be 2. And then derivative of 3e to the negative 5x is going to be negative 15 e to the negative 5x. So I use the chain rule there on the e to the negative 5x. And then derivative of the denominator, we don't know what g of x is, but we do know what g prime of x is here. That's given right there. So that's just going to be 1 over x plus 4 cosine of 5 over x. So again, we don't know what g of x is, but we are given g prime of x, and that's what we want in the denominator. So be careful that you don't take the derivative of g prime of x. That's what we want there. So trying to evaluate this now using direct substitution. We can't actually plug in infinity, but we can think about what happens as x gets really big. Here we get a big negative exponent, which is going to make that go to 0. So our numerator is going to go to 2 because it's 2 minus 0. Then 1 over x is going to go to 0. So x is getting really big, so 1 over infinity is 0. 5 over x is going to go to 0. So we're taking the cosine of 0, which is 1. So we have 4 times 1, which is 4. And that's going to give us 1/2. All right, so the first BC question here is actually going to be the most complicated of them. I do want to point out that this is a calculator question. I forgot to put the little icon here for the calculator, but it is a calculator question. We are looking for the second derivative of y with respect to x, and we are given the first derivatives of x with respect to theta and y with respect to theta. So remember, to find the second derivative of y with respect to x, we are going to take the derivative with respect to theta of dy dx. And we have to do it that way because when we get dy dx, that's going to be in terms of theta. And since we want the second derivative with respect to x, we have to then take the derivative dx d theta, and we're going to divide by that. So this is just a formula that you can memorize. You can understand why we're doing it. Regardless of how you know it, you need to do that. So first of all, dy dx is going to be given by dy d theta divided by dx d theta. So let me get that on here. Dy dx is equal to dy d theta, which is sine of theta plus theta cosine of theta, divided by dx d theta. So cosine of theta minus theta sine of theta. Okay, so that's our first derivative. Then the second derivative is going to be the derivative with respect to theta at this point. And I'm actually going to write that down here first, at theta equals 4. So that's going to be the derivative with respect to theta of dy dx. So sine of theta plus theta cosine of theta over cosine of theta minus theta sine of theta. And we're going to evaluate that at theta equals 4 and take that and divide it by the derivative of x with respect to theta. So that's going to be cosine of theta minus theta sine of theta evaluated at theta equals 4. And this is why I pointed out that this is a calculator question. Taking this derivative right here is pretty complicated. We would have to use a quotient rule. And then within the quotient rule, we have products. So we would have to use a product rule while we're doing the quotient rule. And that becomes a really complicated derivative. It's definitely doable, definitely something that you should be able to do. But since it's a calculator problem, we can put our calculator to work and have it take that derivative for us. So I'm going to move over to the calculator and go through the steps on how I'm going to do that. Okay, so in my graph, in my calculator, I've put in for y1 the expression we had for dy d theta, but I am going to graph this in the xy coordinate plane. So notice that I replaced the thetas with x's. So in this picture here, just picture the x's are thetas. And y2 is dx d theta. And then in y3, this is actually dy dx because I'm taking dy d theta divided by dx d theta. And so instead of typing out dy d theta and dx d theta again, what I did here is I used a trick and just put y1 and y2. So you can get to those variables by going to the vars menu, going over to yvars, and going to the function, and that gives you your y variables there. So we can use y1 and y2 because we have expressions stored for y1 and y2. So when we go to the graph, the first thing we want is the derivative of dy dx evaluated at theta equals 4. So on my graph, I'm going to go second calc derivative, and I want the derivative of dy d theta. I put that in for y3, so make sure you select y3 because we got 3 different graphs. If you take the derivative of the wrong one, obviously you're going to get a wrong answer. And then you want to type in 4 because we want the derivative at 4 and hit enter. So that answer, 3.195, I want to store it in my calculator because I'm going to use that to get my final answer. So I'm going to hit second, quit, go to the home screen, and second answer, store alpha A. And that's going to store the 3.195 for the variable A. So rather than typing in that number, I can just type in A to do my computation later. The other thing I need is I need the value of dx d theta at 4. All right, so keep in mind what I have in here for y2 is dx d theta, and I want to know what that is at x equals, or at theta equals 4. Don't take the derivative of that. We don't need the derivative of dx d theta. That would be the second derivative, and we don't need that. We just need the value of dx d theta at 4. So if I go to my graph and I trace and type in 4, that's going to be 2.3735 and so on. Kind of a weird thing about the graphing calculator, I can't directly store that 2.373 and so on for a variable. So the way I'm going to handle that is I'm actually going to go to the home screen and I'm going to store 4 for x. Okay, so 4 is stored into my calculator for x. And then I want to know what dx d theta is at 4. So remember dx d theta I stored for y2. So I'm going to go to the vars menu, go over to yvars, and select y2. And with 4 stored for x, now it's going to tell me what y2 is, or dx d theta is, at 4. So that's going to be 2.373, and so on. That's the value we got when we traced. All right, so in order to use that, I'm going to store that answer for B. So remember what we have stored in our calculator now. A is the derivative of dy dx evaluated at theta equals 4. So we took the derivative with respect to theta, we evaluated that at 4. And then for B, we have dx d theta evaluated at 4. So our second derivative with respect to x then is going to be A divided by B, which is 1.346, and so on. So if I go look at what our options were, 1.346 is going to be option C. So moving on to the second BC question, we have a polar curve that's defined r in terms of theta. Theta values greater than 0, greater than or equal to 0. And the question is, what's the instantaneous rate of change of r with respect to theta when theta equals 2? So rate of change of r with respect to theta is dr d theta. And we want to know what that is when theta equals 2. So this is really just a straightforward derivative. So dr d theta, that's the derivative of the left side with respect to theta, is equal to, we're going to have to use a quotient rule here. So derivative of the top times the bottom plus the top times the derivative of the bottom, and then all over the bottom squared. And we want to know what that is at theta equals 2. So I'm going to jump back up to where I wrote that, and we'll plug in 2. So we have 10 times 2 squared plus 1 is 5, plus 10 times 2 is 20, times 2 times 2 is 4, all over 2 squared plus 1 is 5, squared is 25. So we've got 50 plus 80. 50 plus 80 is 130 over 25. That can reduce by 5, and we get 26 fifths. I do want to point out that we can interpret this derivative if we know a little bit more information. If we plug in 2 for theta in r, so r of 2 is equal to 20 over 5, which is 4. Since the r value is positive and dr d theta is positive, r is positive and increasing, which means that r is getting bigger in an absolute value sense, which means that if we were modeling motion with this, the object would be moving away from the origin. All right, last question. We have a polar curve given by r equals f of theta. The line tangent to the polar curve at theta equals pi over 3 is horizontal. So the tangent line at theta equals pi over 3 is horizontal. Which of the following must be true? Well, what we need to keep in mind is a horizontal line has a slope of 0. So what this is telling us is that dy dx is equal to 0. And remember, dy dx is dy d theta over dx d theta. And the only way for that to equal 0 is if the numerator equals 0. So by telling us that the tangent to the curve is horizontal, we know the slope is 0, which ultimately tells us that dy d theta is 0 at that point. So let me be a little more specific here. At theta equals pi over 3, that's going to equal 0. So then the question says, which of the following must be true? So looking through the options here, we've got a few choices. So f of pi over 3 equals 0. That doesn't have to be true. F prime of pi over 3 equals 0. So remember, f is the value of r. So this right here, the derivative of that is going to be dr d theta, and we know that dy d theta has to equal 0. So this doesn't have to be true. In fact, it's likely that it's not true. So this doesn't have to be true. So then looking at the other options here, these are not immediately obvious, but what we do know is that y equals r sine of theta. So if we're trying to find dy d theta, this equation here is going to be useful. If we take the derivative of this, let's keep in mind that r is a function and sine of theta is a function. So dy d theta is going to equal the derivative of the first, so dr d theta, times the second, sine of theta, plus the first, r, times the derivative of the second, which is cosine of theta. And since theta is pi over 3, we can plug that in for sine and cosine there. So at pi over 3, we're going to have dr d theta, so dr d theta, remember I mentioned this up here, r is equal to f, so the derivative of r, dr d theta, is the same as the derivative of f. So this is going to be f prime of pi over 3. That's the derivative of r with respect to theta at pi over 3, times the sine of pi over 3. So pi over 3, 1, 2, square root of 3. So sine of pi over 3 is going to be square root of 3 over 2 plus r. So r is just f of pi over 3 times the cosine of theta. Cosine of theta is, or cosine of pi over 3 is going to be 1/2. So matching that up with our options here, it looks like D is going to be our answer.